Right, so we're looking at Chemistry Unit 1, higher tier. You can read for yourself. It's the May-June 2012. So you should have had a chance to look at this exam already. Let's have a look and see what the answers should be. So we've got the mark scheme on the right for us just to help us out. First one should be nice and straightforward. It's asking us which one can be found uncombined in the Earth's crust. The big clue here is right there. Least reactive is gold, so that should be option B. Metals are extracted by the reduction of their ores. State the meaning of the term reduction. So this is knowing one of our key words. Reduction is all about oxygen, and it's the loss or removing of oxygen, as we look at later on. It can also be in terms of electrons. Oxidation is loss. Oh well, yeah, oxidation is loss of electrons. Reduction is gain of electrons. Just checking my subject knowledge there for a second, as you do. So that's what this bit here is talking about in the acceptable answers, because you might go on to study further stuff and then take all your tests at the same time. Right, on part C. Why is electrolysis used for aluminium but not for iron? A couple of routes you can go down here. I think one of the most obvious ones, given the information that you've just had in the first part, would be that aluminium is higher in the reactivity series. Higher than what? Higher than carbon. So it means that, using the stuff we talk about in class, if carbon walks in and tries to push aluminium away from whatever it's joined onto, aluminium's just going to laugh at it for not being reactive enough. It's not going to be able to displace it. Or one of the other things that you might be thinking about is the opposite, that iron is lower in the reactivity series. I'm throwing in an extra point. So the interesting things here are things like electrolysis is a better or more powerful means of reduction. So it's gonna have more energy to give to it, so it can separate more reactive compounds. Or we can have that iron can be reduced by carbon, so it will work with carbon. There's an obvious link into cost here. Carbon's pretty cheap. Using electricity is going to be expensive on a big case. So we're looking for a quick improvement here for your work. Maybe you're thinking of putting that aluminium is higher in the reactivity series, so you can't use carbon. Whereas iron you could use carbon, and that is cheaper. For D, explain why the aluminium alloy is stronger than pure aluminium. You'll hopefully remember when you did this in class that you've got these little circles, these layers of circles, and that in a pure metal they can slide over each other. So when we're talking about aluminium being stronger as the alloy, then we're thinking about these magnesium or aluminium ions. Ions. You can call them atoms or particles, and they're different sizes compared to each other. Because they're different sizes, we've got layers that can't slide over each other. They jam up. Okay. So obviously you can see in the acceptable answers there, we've got all the stuff about sheets and rows and thinking about sliding over each other. Look at that, penalise molecules only once. So try and put in some of the right words, because they're magnesium atoms, or if you've looked at it in terms of Chemistry Unit 2, they are cations, they're charged ions. Particles is acceptable as well, but not molecules. Molecules is where they're joined together, it's covalent bonding, so steer away from that one. Word equation, over here on the right hand side, it shows you it's balanced. How am I getting to that point, you might be asking? Well, it's got the right hand side done for you. If I want to get to 2 lots of Al2, there's aluminium twice, and I've got 2 lots of it, so 2 lots of 2 is 4. And then on this side over here, I need to know how many oxygens. So there's 3 oxygens on this part, and I've got that whole molecule twice, which means that I've got 2 lots of 3, which is going to be 6. So I'm going to want 3 lots of 2 here to make 6 as well, to make sure it's the same on both sides. And you get a mark for each one there. So, second question, mark scheme updated. Looking at the Earth's atmosphere, then explain why it's difficult to be precise about the early atmosphere. The easiest, most obvious answer that we're looking for, nobody was there. Which then obviously leads on to another point, and you might have missed off adding a second point. So you won't have any written records, or there won't be any evidence, because that's what scientists like. Or even if you're looking at things like ice cores, which we used to look at previous historical measurements before we started taking scientific measurements, we can't find ice old enough for that sort of time. It would have melted, and even rocks get worn away and destroyed. So, part B, how did the oceans form and affect the atmosphere? There's two ways you can go on that. Water vapour would mean that, water vapour turning into oceans would mean that it's no longer in the atmosphere. So we've got water vapour decreasing, and carbon dioxide will also decrease because carbon dioxide dissolves in water. So that's where over half of the carbon dioxide went to. Part C, plants. Instantly you're thinking photosynthesis, aren't you? And look, there it is on the mark scheme. Magic. Explain how the growth of plants affected the composition of the atmosphere. Well, we've already got a mark for saying photosynthesis because you're a genius like that. And you just describe what it does. So it takes in the carbon dioxide and it is releasing oxygen. One of the things that you need to know then about the atmosphere is some of the percentages of the gases. Nitrogen 78%, oxygen 21%, and here's our buddy carbon dioxide. It's nowhere near what people first think it is. It's only 0.04%, so it's quite a nice question to put in there to test you. Part E, other causes of increasing carbon dioxide apart from fossil fuels, which is a very obvious one because we do that a lot. Cutting down trees, deforestation, volcanoes, we still have them, they're still producing carbon dioxide like the early atmosphere. Respiration, because every living thing respires, and also an increase in the temperature. Why an increase in the temperature? Carbon dioxide can come out of solution from water, so as you increase the temperature, less gases dissolve. I'm impressed if you got that one, to be honest. But you only need one of the ones from above. Skipping past the blank pages. Hydrocarbons. So for 3A part 1, using the table, we want to know which fractions does the demand exceed the supply. And it's just looking up here. So we've got 2, we want 6, so LPG's on my list. So I'm instantly looking at B or C, and looking what else have we got more of in demand and less of in supply. So I've got lots of demand for petrol, so petrol's got to be in there too. It's still B or C. Kerosene 11, 16, I've got plenty of that to go around. It can't be C, let's just double check. It should be diesel, that's got more on the right hand side, and look, it has. So we're looking for option B. Why do we need cracking? Be careful, you've got to say two things here, 2 marks. So cracking is useful because it will take the longer molecules, which aren't so useful. Look at all these things you can say about it: lower value, less useful, less demand, and then turn them into the small molecules, which are needed, and you've got to imply something along those lines. You can't just say it makes small molecules, you've got to be saying they're good for fuels. You could name specific uses of fuel. You could talk about, in this mark up here, using up specific things that you've got an excess amount of. So the table here said kerosene, look, oh, I've got more of that than I need, I can use some of that up. I can make some of the petrol that's in demand. There's a lot of clues there in the question that can help you. For part B, we've got here the number of molecules increasing as we're going down the fractionating column, with bitumen at the bottom and the gases at the top. What conclusion can we get from that? Well, we can narrow it down a little bit. The number of hydrogen atoms in the molecules remains the same. That's the number of carbon. Yeah, that's not going to happen, is it? Because more carbons, they get more hydrogens, because it's a hydrocarbon. They follow that pattern, don't they? CnH2n or CnH2n plus 2. The boiling point of the hydrocarbon increases. Well, that's true, isn't it? Because at the bottom, bitumen, it doesn't even evaporate even when it's been heated at the fractionating column. Double check in C. The hydrocarbon becomes easier to burn. It's difficult to set fire to roads, isn't it? So that's not true, with bitumen being on the bottom for making roads. Viscosity is a nice word. That means how thick it is, like when people say blood is thicker than water. And obviously bitumen is much thicker. There's that investigation going on where there's blobs of tar that are dripping, and they only drop once every stupid number of years, 10 or more years or something like that. So it's just about as not viscous as, actually just about as viscous as you can get. So statement D can't be true. Part C, the formula for this molecule is nice and easy. There's 1, 2 carbons, and there's 1, 2, 3, 4 hydrogens. So we're looking at C2, H4 magic. Easy marks that, isn't it? This one here, loads of people would get wrong. In class, we'll look at drawing something like this. So we can say you can get N for any number of these monomers, and don't forget that's given to you right up here. Ta-da! And so we can put that on this side here, an arrow for a reaction, and then when we're looking at what's being formed on the right hand side for the polymer, we're breaking the double bond. We notice the difference here to here, and then we've extended the bonds from either side of the carbon outside of these brackets, and you've got brackets there to show that this unit here is being repeated however many times, so N is any number you can have. You can also include it as this sort of thing here. Bit easier to draw, but most people have seen it like this because there are other questions you can ask like this, where you can get things like CH3s or CLs replacing some of the H's, and you can look for the patterns in them. For D, explain why some people are concerned about the increase in carbon dioxide. Carbon dioxide is a greenhouse gas. It traps heat, and then that is going to be linked then to global warming. So a reference to each. Don't even go near saying the ozone layer. It's not something we cover. It's not got a link to anything like that. So just, yeah, ignore it. You'll lose if you say anything about ozone layers in your GCSEs at the moment. So on to part 2. Notice part 1 and part 2. They're part 1 and part 2 because they link together. So this one is talking about burning hydrocarbons as well, and pollution that comes from them. So you should be thinking, what other sorts of pollution are there? And you're looking at sulfur. When you burn sulfur, any combustion reaction is combining it with oxygen. It's an oxidation reaction, so we're going to end up with sulfur dioxide being formed. Ta-da! Look, there it is on the mark scheme. What problem can that do? Well, sulfur dioxide can dissolve and it can form sulfuric acid. So we get to acid rain, and then you can start talking about the effect of acid. You'll need 2 of those to get the 2 marks over here. Question 4. We're looking first of all at this table and which one's true, which line's true. Chalk is sedimentary, so it's got to be A or B. Marble is not sedimentary, it's metamorphic. You make it from chalk, so we know it's line C. Nice and easy. For B, looking at the reactions of calcium compounds, get used to this, learn this stuff off by heart. This is something they'd love to ask you about for equations and balancing equations, and about lime water and limestone and its reactions. Should be your best mate. So how could you show that a reaction with calcium carbonate has taken place? Well, you can look here and see, right, what's happened from there to there. Right, I've lost a C and 2 O's, I've lost carbon dioxide. How could I test for carbon dioxide? In comes our old buddy, we could have lime water, and then that turning cloudy or milky. What else could I look at? Well, if you've looked at additional science, you might be thinking calcium weighs 40 for its atomic mass, carbon weighs 12, oxygen 3 lots of 16 there. That gives that an overall mass of 100, and then this one is going to be 40 and 16, that gives me 56. Each atom's going to weigh less, so this is going to have lost mass. How can I show that in the real world? I could get out some scales, a balance. I could weigh it before, weigh it afterwards, and it's going to lose some of that mass because it's giving off carbon dioxide. I'll be impressed if you're getting it that way around. For part 2, these ones are always ones that trick up some of our brightest. So you describe what you would observe if this is happening. So you're adding this step by step. You're not getting the calcium oxide that you heated in class with your Bunsen burner. You've got to light some limestone, put it on top of a gauze. You heated it for several minutes. It looks pretty similar, but it's the stuff that's going to blind you if you get it in your eyes. It's the calcium oxide. It looks pretty much the same. If you add a few drops of water, not just dunking it into your test tube of water to make your lime water, if you just add a few drops, you'll see it reaction. It's an exothermic reaction, so it's going to get hot. So it's really easy to see things like fizzing and steam and swelling, and it crumbling to a powder. If you dump loads of water on it, it turns into lime water, but that's not what the question's asking you. At this point, you need to swap to the next video because my 15 minutes of fame are up. And we're back, aren't we? Yeah, I've got 15 minutes limited on my account that I use. So where are we up to? Writing a balanced equation, nice and simple. You've got the calcium hydroxide given to you there, and you know what carbon dioxide is. So that's how we do the left-hand side. Easy marks. Slightly harder right-hand side. Calcium carbonate there, given to you, but you've got to use a little bit of your nouns to balance it and realise that there's an H2 and an O missing that should be on the right. So again, a little bit trickier, but you should be able to spot that if you're looking at balancing it, like it says balanced equation. Right, so, skipping ahead a little bit. Common name for calcium hydroxide, lime water. I think we've mentioned that in more than enough at the moment. This question comes up all the time. Start getting it programmed into your head. The impurity in fossil fuels is sulfur. The sulfur burns in oxygen to make sulfur dioxide. Sulfur dioxide is going to react with the limestone because it's an acidic gas, and the limestone is a base. Why is it a base and not an alkali like it says here? It's not ignoring alkali. Alkalis dissolve, bases don't. Lime water doesn't dissolve, so it's a base. You could be an absolute geek and tell me what the salt is. In this case, it's the calcium from the calcium carbonate, and it's reacting with the sulfur dioxide, the sulfuric acid it makes, which makes a sulfate. That's how you get that one. And it's a neutralisation reaction. What's my easiest answer? Look at this. Neutralises acid gases equals 2 marks. Fandabidozy. Moving on, question 5, electrolysis. Hazard of chlorine, it's toxic, it's poisonous, that's nice and simple. Test for chlorine, don't put squeaky pop, don't be a muppet. Damp blue litmus paper, you can get away with litmus paper, but let's be good at this. Damp blue litmus paper turns it red because it makes it an acid, and then white because it bleaches it. So, you can get away with litmus paper turns white, but let's be good. State of use of chlorine, just don't write swimming pools, okay? Look here, ignore swimming pools. It kills microorganisms, it's used for sterilising things, it's not used for making a swimming pool itself. This one here, you might want to look at your revision guide to get this bit straight. Electrolysis is splitting things with electricity. You can't get sodium coming out because it's far too reactive, it's set on fire in the water and it'd give out hydrogen. But that tells you what the gas over here would be, it's hydrogen, H2. You can get the chlorine coming out, the Cl2, which we're talking about testing for here. That should be a clue that the answer is going to be in here too. And then that would leave some Na and some OHs from over here, which gives us the NaOH, which you see here. Balancing it, I've got Cl2, so I'm going to need 2 Cls. And because I've got 2 Nas, I'm going to need 2 NaOH here, which means I'm going to need 2 H2Os. This one here, people generally bomb at because it's a 6 marker and they don't like to answer it, but it's actually just a little bit of data analysis. Let's look at what we do for it and see just how easy it is. So have a look here, time. What's happened from here to here? We've doubled the time. What's happened from here to here? Lame answer says it's increased. If you notice, that's doubled and that's doubled, so we can say it's proportional, or we can say if one's doubled, the other's doubled. And that's where we can get really good at our answers. If we're looking at current, if we look at the same amount of time in 1 and 3, and the current, it's gone up by half. It's gone up by 0.25. And look how much the hydrogen's gone up by. It's gone up by half. Another mathematical link there. And then another one just for good measure. Look at this. 20 and 10, 40 and 20, 30 and 15. What have they got all in common? It's twice as much hydrogen as oxygen, which should make sense. H2O, if we look at it here, is made out of 2 hydrogens for every oxygen, which is why this gas column here for hydrogen is twice as big as the oxygen one. What does a 6 mark answer look like? As easy as this, look at it. The volume of hydrogen is twice the volume of oxygen, and as time doubles, the volume of gas doubles, or as you increase the current by 1.5, the volume of gas increases by 1.5. Just looking at those details, nothing else, no hardcore science involved in it. He says, the science teacher. 6A, last one. I know we're getting there. It's good. Renewable and non-renewable, nicely highlighted, telling us the difference. So I think most people describe what the word means rather than giving an example, but you can get a mark for the example. Non-renewable cannot be replaced. Don't even start thinking about can't be used again or anything like that. That's reusable. It's a different word. Don't use it. And then describing what renewable is, it can be replaced again relatively quickly, as in like it can be regrown. For our 6 marker, again straightforward, not too complicated science. We're looking at advantages and disadvantages of using bioethanol, so split it up into 2 nice easy chunks, whether it's a table or paragraphs. So advantages, bioethanol is renewable. That's a good thing, isn't it? You can grow them again quickly, so there's a short lead time of making more. It means that what you're using fossil fuels for, you can keep using them for, and it can last longer before you run out. Because you're taking carbon dioxide out of the air to grow the crops and then burning it, you could say it's carbon neutral. And it doesn't have the sulfur impurities that we looked at when we were looking at the chimneys earlier on. A lot of people also like to remember that the alcohol burns completely. A nice clear blue flame. It's quite difficult to see, almost a bit dangerous really, because you can't see that smoky yellow flame that you might get from petrol. Looking at the disadvantages, you just don't find it in the petrol stations. It takes up space for crops, which obviously either needs trees and things cutting down, land clearing, or takes up space where you'd otherwise be growing crops. And your car and a lot of other cars on the road won't run on it already. How do I get 6 marks? Look at this bit here. Give me a few advantages and disadvantages with some key words, some science words like carbon dioxide, renewable, that sort of thing. Relatively straightforward, hopefully, that you can see there, at least if you didn't get it in the first time round. And look at that, an exciting bus. It's using hydrogen. It's just an excuse to give you this equation. H2 plus O2 gives us H2O. You get a mark for this side, you get a mark for that side, and the third mark is for balancing it. H2O's only got 1 oxygen. This comes as 2 oxygens, so let's put a big 2 in front of it to get 2 whole units of this. Because I've got 2 whole units of this, I've got 2 lots of that 2, and that makes 4 in total, so we have 2 lots of the 2 here, 4 in total, balanced on both sides. We know hydrogen's explosive because you can't stop telling me about squeaky pops, but they take that answer away from us, so I want to know, why don't we use it for buses? One of the easiest things you might say, you just don't see it in petrol stations. Or the gases, can escape quite easily. Just think about your balloons that you get for your birthday and how quickly they can go down. You can talk about the technology used to store it, or the fact that you've got to use electricity to make it, but I think these 2 here are the most likely answers. Should be able to top that up and give me a score out of 60. If you do need any more help, come along and see one of us lovely science teachers. You might be wondering what your grade is after doing that, so we'll bring in our grade boundaries. Don't worry, you're not doing Arabic, I know that. Let's have a look, see here. So you're on this row. You're doing chemistry, no, that's chemistry 2, chemistry 1, there we are. Chemistry 1, out of 60 marks, if you got 44, you got an A star. If you got over 36, you got an A. If you got over 28, you got a B. If you got over 21, you got a C. 14 for a D. 10 for an E. And then if you didn't get 10, unfortunately, you got a U. Right, job done. See you later.